Welcome to this section on the course on Introduction to Measure Theory, and this section is titled Construction of Lebesgue Measure. The idea of Lebesgue measure actually emerged in attempts to assign an idea of the length to any set of real numbers in order to extend the scope of the concept of integration to larger class of functions and overcome some limitations of the Riemann theory of integration. Lebesgue measure in fact is a set function. By a set function, we mean an extended real-built function f defined on a class of sets cursive C. A set function f is called non-negative if f values are non-negative. It is called monotonic if f of a is less or equal to f of b for members a and b in cursive C with a contained in b. It is called finitely additive if for any finite divisions of class a1, a2 up to an of C, whose union is also a member of C, we have f image of the union is equal to sum of the f values. Further, f is called countable additive if for a countable class of members of C which are disjoint and whose union is a member of C, we have f value of the union is equal to the sum of the f values. Also, f will be called countably subadditive if for a countable class of members in C whose union is also in C but the class is not necessarily disjoint, we have f value of the union is less or equal to sum of the f values. Here we give two examples of set functions. First, we consider a class cursive C of members an where an are the sets containing the first and natural numbers, and we define a function f on cursive C by f of an is equal to n into n plus 1 by 2, that is the sum of the members of an. Then we leave a problem for the readers that f is a non-negative monotonic set function. The second example is on the class C of all subsets of R, and we define a function z on C by z of e is equal to plus infinity if e is infinite and is equal to number of elements in e if e is finite. So we leave another problem for the learners. Z is a non-negative, monotonic and countably additive set function. Now we can talk about another set function which is named as length function. Suppose we have the class of all intervals named cursive I, and we define a function L on cursive I by L of a member I of I is equal to length of I. So by length of interval what we mean is this one: if L I is a finite interval of any of this type, then length of a I is equal to b minus a. And if I is an infinite interval, then we assign the length of that interval to be equal to plus infinity. So we can easily see that L is a non-negative, monotonic and finitely additive set function. The natural question that arises here is that can we extend the notion of length to larger classes of sets of real numbers? For example, suppose we consider the class of all open sets named as cursive O, and we can define the length of any member z of O to be the sum of the lengths of all open intervals of which it is composed. And because every open set of R is a countable disjoint union of open intervals, so this definition of length of Z appears to be consistent. However, the class of open sets is too small a class to serve our purposes, and so we eye on much larger classes of sets of R. In fact, our aim is to construct a set function M which is defined for all subsets of R, which is an extension of the length function, which is countably additive and which is translational invariant. That is, m of a plus x is equal to m of a for a real number x. So we shall proceed in this direction in the next section by first defining a set function for all subsets of R, and that set function will be called Lebesgue outer measure. We conclude this section by pausing 2 problems for the readers. Try to think of a set function which is defined for all subsets of R, which is countably additive and translational invariant. And you can think of a set function defined for all subsets of R, which is again countably additive but not translational invariant. Thank you.